The topic that I got was electrochemistry. This is a picture of an electrochemical cell, and the first statement given to us is, it is observed that when silver metal is placed in aqueous thallium-1 fluoride, no reaction occurs. When the switch is closed in the cell represented above, the voltage reading is positive 1.14 volts. Right away, we know that this is an electrolytic cell because we need a power source to make it run. This also tells us that when solid silver is in a thallium fluoride solution, it is not a spontaneous reaction. An electron will not leave the silver to form solid thallium in a silver solution, so the reaction must occur the other way around, telling us that silver must be the reduction half reaction, because must want to gain an electron. Remember, Leo the lion goes first. When we refer to the standard reduction potentials table we see that the half reaction for silver is this half reaction right here. Since this is the reduction, it must occur in the cathode because anox, red cat, reduction cathode, oxidation anode. So since this is the cathode, the thallium cell must be the oxidation reaction which occurs in the anode. This is the answer to part C. Also notice that in the picture, I have electrons flowing from the anode to the cathode. Electrons always flow from the anode to the cathode. And remember that the salt bridge is in the middle to balance out the electrons. So part B asks for the equation for the overall reaction in the cell. To get the overall reaction that occurs in the cell, we must simply add the two half reactions together. Here is the thallium reaction. Since it is the oxidation, this is what the reaction must be. When you add these together, the electrons on both sides cancel out, and this right here is the reaction that you are left with. Part D of the question says that the standard reduction potential of the reaction platinum 2 plus 2 electrons goes to platinum solid is 1.2 volts. Assume that the electrodes of pure platinum, silver, and nickel are available, as well as 1 molar solutions of their salts. 3 different electrochemical cells can be constructed using these materials. Identify the 2 metals that when used to make an electrochemical cell would produce the cell with the largest voltage. Explain how you arrived at your answer. Right here, I put the standard reduction potentials of all of these metals. And remember that these are the reduction potentials. They are the E reds, not the E oxides. To get the E of oxidation, you just change the sign from either positive to negative or negative to positive. To find the E cell, we must add E oxidation plus 1 E red. What you want to do is get the largest possible E cell. So you want the biggest E oxidation and the biggest E reduction. For us, there is one reduction that is negative. So that must mean that it has the highest E oxidation because it will be a positive 0.25, where silver will be a negative 0.8 and platinum will be a negative 1.2. The highest E red value is platinum, which is 1.2. So you simply add those together and you get your value of 1.45, and that is the largest voltage we could make. The last question says, predict whether platinum metal will react when it is placed in a 1 molar solution of silver nitrate. Justify your answer. So if solid platinum metal is added to a solution of silver nitrate, the only redox reaction that could happen would be for Ag plus to be reduced, which means that it would gain an electron. And so what we need to do is we need to find the E cell. If it is negative E cell, it is not spontaneous, and if it is a positive E cell, then it is spontaneous, so the reaction will happen. Again, the equation to find the E cell is E oxidation plus E reduction. So for us, the oxidation would be platinum, since silver would have to be reduced. So we are given the reduction potential of platinum, which is 1.2 volts. Since it is the oxidation, we need the E-ox, so it is negative 1.2 volts. And then we're going to add the E reduction of silver, which is 0.8 volts, and you get negative 0.4 volts, which means that is non-spontaneous, so the platinum metal will not react when placed in a 1 molar solution of silver nitrate. So here are most of the equations given to us at the same time as we did this chapter. So the first equation is delta G equals negative NFE, and the E is the E of cell. So N is the number of electrons being transferred, and F is a constant, 96,485 coulombs per mole, or 96,485 joules per volt mole, since a coulomb is just a joule per volt. Another equation is delta G equals delta G standard plus RT ln Q, and R is 8.3144 joules per mole Kelvin. Another equation is delta G equals negative RT ln K. And the Nernst equation is E equals the E standard minus RT over NF ln Q. And we have all the same variables and constants used as above. But at 25 degrees Celsius, this is a specific equation that you can also use. E equals E standard minus 0.0592 over N times log of Q. Notice the difference between ln Q and log Q here. Another thing we talked about was concentration cells, in which you have the same substance on both sides of the cell, but one is more concentrated than the other. And for that, the Q always equals the concentration of the dilute solution over the concentration of the more concentrated solution. Oh, and also, the spontaneous cells can be called galvanic or voltaic cells, whereas the non-spontaneous cells are called electrolytic cells. So that's just the distinction. And oftentimes electrolytic cells are used with molten ionic solids because the water would get in the way if it was aqueous solution. Like if the water may be reduced or oxidized instead of what you actually want to be reduced or oxidized. And work, which is the work provided by the external power source, like the battery or whatever you have, one equation is work equals NFE external, and the E is of the external power source, and the N is still the number of electrons, and F is still the same constant. 1 watt equals 1 joule per second, and 1 kilowatt hour is 3.6 times 10 to the 6 joules. And the last little thing that you can set up for Stoic, which is just like a plug and chug, is this little chart right here. So you either start with your current times your time, or your grams of substance, oxidized or reduced, or anything in the middle, and you just simply go down the line or go backwards or whatever. So you have your current, which is in amperes, times your time. So your time is in seconds. Sorry, I forgot to write that. And then from there you go to your quality of charge, which is in coulombs. And remember the Faraday constant is the same one given before, 96,485. And then you go to your moles of electrons, which is in Faradays. From there you're going to take it onto your moles of your substance that is either being oxidized and reduced. And then lastly, you are going to take it to your grams of substance being oxidized or reduced. If they only ask for moles of your substance, obviously that's where you're going to stop. And if a question that has something like the electrolytic cell is 85% efficient, if you are given your current and your time, after you multiply those two together to get your coulombs, you are going to multiply that by your 0.85 or your point whatever percentage that you are given. So you take that into account and then you just plug and chug just like you would do before if you didn't have that.